On October 2nd, something fast, incredibly fast, streaked across the Martian sky. An amateur astrophotographer named Stephen Burns noticed it in NASA's raw Perseverance rover images. He created a time lapse, 9 minutes of data, compressed, and there it was, moving at 60 kilometers per second against the normal motion of the stars. But here's where it gets weird. Other users started analyzing the same images, and they claimed to see multiple objects, not just one. Multiple fast-moving anomalies in the October 3rd data, plus a mysterious green flash that nobody can explain. NASA scheduled this observation. Multiple Mars orbiters were supposed to capture the closest images ever taken of an interstellar object, the Haya-Rusi camera, capable of 30-kilometer resolution, the SS Mars Express, the ExoMars Trace Gas Orbiter, all pointed at 3I Atlas during its October 3rd flyby, and then silence. No official images, no data release, nothing. Meanwhile, Harvard's Avi Loeb just published something that's making the entire astronomical community uncomfortable. This object, 3I Atlas, might have been the source of the famous 1977 WOW signal. The chance of that being coincidence? 0.6%. But the WOW signal connection is just the beginning, because 3I Atlas is breaking every single rule we have for how comets behave. It's producing industrial-grade nickel alloys in space. Its tail points the wrong direction, it's green when it shouldn't be green, and it's following a trajectory so perfectly aligned with our planet that the odds are astronomical. Some are calling it the largest interstellar object ever detected. Others are calling it impossible. Avi Loeb is calling it potentially artificial. And right now it's behind the sun where we can't see it, hidden, approaching its closest point to our star. What happens when it comes back out? Before we dive deeper, if you're finding this fascinating, hit that like button and subscribe so you don't miss what's coming next. And tell me in the comments where you're listening from, what time it is there, and whether you think we're seeing one object or multiple. And if you want to help this community grow, share this on X, Facebook, Reddit, or your messenger. Thank you for always having our back. Chapter 1. Wait, there are multiple objects? Let's go back to October 2nd. Stephen Burns wasn't looking for anything extraordinary. He was simply processing the raw image data that NASA makes publicly available from the Perseverance rover. The rover had been instructed to observe the night sky during a specific window, the window when 3Y Atlas was predicted to pass closest to Mars. Closest being a relative term. We're talking about 29 million kilometers of separation. Burns took 9 minutes of consecutive images and stacked them into an animation. In astrophotography, this technique reveals motion that would be invisible in a single frame. Stars appear to move across the frame due to Mars' rotation, but this was different. Something was cutting across that motion at an angle that made no sense for a background star. The speed was the first clue. At 60 kilometers per second, 3D Atlas moves faster than nearly anything in our solar system. For comparison, Earth orbits the Sun at about 30 kilometers per second. The Parker Solar Probe, humanity's fastest spacecraft, reaches 192 kilometers per second only at its closest approach to the Sun. But 3Y Atlas maintains this blistering pace throughout its journey. Burns posted his animation online. Within hours, other amateur astronomers began their own analysis. And that's when someone named Nachthafer, a German username meaning night monkey, made a claim that sent ripples through the observing community. In the pictures from October 3rd, Nachthafer wrote, "You can even see multiple comets, not one object multiple." Another user, Alexander Ferrum, pointed out something else. What is the flash at second 0003 marked with green? Go back and watch Burns' animation frame by frame. There, at the 3-second mark, a brief green luminosity appears. It's not a camera artifact. It's not a cosmic ray hit, which would appear as a single bright pixel. This is a diffuse glow, localized but distinct. Green light in space has specific causes. On Earth, we associate it with auroras, with copper burning, with certain bioluminescent organisms. In space, green emission typically comes from oxygen or from a molecule called dicarbon, two carbon atoms bonded together. Comets sometimes glow green when solar radiation excites dicarbon in their comas. But here's the problem. Spectroscopic analysis of 3I Atlas from the Very Large Telescope showed virtually no dicarbon. The object is what astronomers call carbon chain depleted. It shouldn't be glowing green, yet photographs from ground-based telescopes in early September clearly showed a green hue developing around the object. The green flash in the Mars images, if real, adds another layer to this mystery. Now, about those multiple objects, this is where things get speculative, but the speculation is coming from people with telescopes and image processing software, not from people making things up. When you stabilize the star field in Burns's animation, when you account for Mars's rotation and the motion of the primary object, there appear to be at least one or two additional points of light moving at different velocities. Could these be imaging artifacts? Absolutely. Could they be background asteroids that just happen to be in the frame? Possibly. Could they be separate objects? Or even smaller objects accompanying 3I Atlas? That's the question nobody can answer yet, because NASA hasn't released the data. The Mars Reconnaissance Orbiter's high-rise camera observed 3I Atlas on October 2nd between 1 and 4 in the morning, Mars local time. The ESA's Trace Gas Orbiter and Mars Express both captured observations on October the 3rd. These weren't casual snapshots. These were coordinated, pre-planned scientific observations designed to gather the highest resolution data ever obtained of an interstellar object. HIRIS, the high-resolution imaging science experiment, can resolve features as small as 30 centimeters on Mars' surface from orbit. When pointed at an object 29 million kilometers away, it should still achieve a resolution of about 30 kilometers per pixel. That means if 3I Atlas has a nucleus 5 kilometers across, as recent estimates suggest, it should appear as a bright cluster of pixels in the Hersey images. More importantly, Hersey would be able to distinguish between a single compact nucleus and a fragmented or multi-component object. If there are multiple pieces, if there's a companion object, if there's anything unusual about the structure, Hersey would see it. So, where are the images? NASA's official statement has been minimal. The Mars orbiters successfully conducted their observations. Data is being processed. Updates will be provided as analysis continues. That was over 24 hours ago. In the world of space imaging, 24 hours is plenty of time to at least preview raw data. Some observers have noted that the United States government has been dealing with various administrative issues that have affected the release of scientific data, but ESA operates independently. They should have no such constraints. Yet ESA's images haven't appeared either. The silence deliberate. And when official channels go quiet, amateur observers start talking. Because here's what we know for certain. The Perseverance rover did capture something. Multiple amateur analysts examining the same publicly available raw data are seeing anomalies. The object or objects moved at velocities consistent with 3I Atlas. And there's that green flash that no one can explain. What we don't know is whether those apparent multiple objects are real, whether they're separate from the main comet, and what NASA and ESA saw with their far more powerful instruments. The October 3rd flyby represented the closest any spacecraft has ever come to an active interstellar object. This was our chance to understand what 3I Atlas really is, to see its structure up close, to determine if it's behaving like a normal comet or like something else entirely. And as we wait for answers, the object itself continues its journey. Right now, it's approaching the sun, moving deeper into the inner solar system where Earth-based telescopes lose sight of it against the solar glare. By late October, it will pass behind the sun from our perspective, completely hidden, and when it emerges in November or December, it will either confirm every natural explanation or it will have done something that comets simply don't do. But before it vanishes, we need to talk about what the Mars observations were really looking for and why the timing of this silence matters more than you might think. Chapter 2. The Mars Blackout. There's a pattern in how space agencies handle sensitive observations. When something routine is captured, the data appears within hours. Raw images populate public databases. Press releases get drafted. Scientists tweet their findings. When something unexpected appears, the silence stretches. The technical explanation for the delay seems on data processing pipelines and calibration requirements. Mars orbiters don't transmit images in real time. They store observations on board, then beam them to Earth during scheduled communication windows. From there, the data moves through various processing stages: geometric correction, radiometric calibration, noise filtering. For a typical surface observation, this takes 6 to 12 hours. For a moving target against the star field, maybe twice that. We're now well past 48 hours since the October 3rd observations, but there's another factor at play, one that doesn't get mentioned in official statements, but filters through the community of researchers who depend on NASA data for their work. Budget constraints and administrative disruptions have created bottlenecks in data release protocols. Not a formal shutdown, but the kind of bureaucratic friction that turns routine processes into delayed ones. Staff working reduced hours, priority systems getting reshuffled, review chains lengthening. ESO operates under different administrative structures, yet their Mars Express and ExoMars Trace Gas Orbiter images haven't appeared either. This suggests either a coordinated decision to withhold preliminary data until full analysis is complete, or technical challenges that both agencies are working through simultaneously. The question becomes, what would be challenging enough to cause this delay? Consider what these instruments were designed to see. The Color and Stereo Surface Imaging System, CASIS, on the Trace Gas Orbiter can resolve features down to about 4.5 meters per pixel when imaging Mars. Pointed at an object 29 million kilometers away, that resolution drops significantly, but the instrument's sensitivity remains high. It's designed to detect subtle color variations in Martian surface materials. If 3I Atlas was shedding multiple types of ice, if it showed compositional variations, if there were structurally distinct regions, CASIS would capture that. Mars Express carries the high-resolution stereo camera, which despite its name focuses on three-dimensional topography. For a distant comet, its stereo capability matters less than its ability to image across multiple wavelengths simultaneously. The camera can distinguish between dust, water, ice, carbon dioxide, ice, and various minerals based on how they reflect different colors of light. Then there's the Mars Reconnaissance Orbiter's HiRISE, which we've mentioned, but here's what we haven't discussed. HiRISE doesn't just take pictures, it collects data across three color bands: blue, green, red, and near infrared. When pointed at a comet, those bands reveal different aspects of composition and activity. Blue, green light interacts with gases in the coma. Red and near infrared penetrate through thin dust, revealing structure beneath. If the comet was releasing jets of material from specific locations on its nucleus, if those jets had different compositions, if the brightness varied across the objects in ways that suggested a non-uniform surface, HiRISE would document all of it. And here's the thing about sensitive images: they sometimes show features that require consultation before release. Not because of conspiracy, but because preliminary observations can be misinterpreted without proper context. If HiRISE captured something that looked unusual, mission scientists would want to rule out instrumental artifacts, cosmic ray hits, or processing errors before making the data public. But while we wait for official channels to open, there's Simeon Schmaus. Schmaus is an astrophotographer who specializes in processing raw planetary data. He's known in the community for his ability to extract signal from noisy images to stabilize shaky video, to bring out subtle features that initial processing misses. On October 1st, a day before Stefan Byrne's October 2nd time lapse, Perseverance captured a series of night sky images. These were posted to NASA's raw image database. As all Perseverance images are, within hours of being received on Earth, Schmaus downloaded them, applied his processing techniques, and claimed to see an early glimpse of 3I Atlas in those frames. The claim hasn't been independently verified. The object would have been extremely faint at that distance and angle, but if legitimate, it suggests the comet was detectable even before the main observation window. More intriguingly, Schmaus noted that the motion he detected didn't perfectly match the predicted trajectory, close but with a slight deviation. He posted his findings on social media stating that more analysis was needed, but the preliminary results were intriguing. Then, like the official sources, he went quiet. Whether he's still analyzing, whether he found something he wants to confirm before discussing publicly, or whether he's been asked to hold off, we don't know. What we do know is that there's a gap between what should be routine disclosure and what's actually happening. A gap between the scheduled observations and the data we can examine. A gap that's filled with amateur discoveries, unexplained green flashes, and claims of multiple objects that nobody can officially confirm or deny. The Perseverance rover continues its surface mission. Its cameras remain functional. Its data continues uploading to the public database. But the specific images from those crucial nights, the ones that matter most, are the ones being scrutinized in silence. By October 29th, 3I Atlas will reach perihelion, its closest approach to the Sun. At that point, it will be entirely behind our star from Earth's perspective, invisible to ground, based telescopes and space-based observatories alike. The window for observation is closing. Whatever NASA and ESA saw, whatever Schmaus found, whatever is happening behind the review processes and data pipelines, the clock is running. Because if there's something unusual about this object, if those multiple points of light are real, if the green flash means something, we need to know before it disappears into solar glare. And if we don't get those answers, we'll have to wait until November, when the comet emerges on the other side, potentially changed by its close encounter with the Sun, potentially having done something that natural comets don't do. But there's another reason the timing matters. Because while we've been focused on what the Mars observations might show, Avi Loeb has been looking backward, tracing 3I Atlas's path, not just through our solar system, but through time. And what he found connects this object to one of the most famous unexplained signals in the history of astronomy. Chapter 3. The Wow. Signal bombshell, August 15th, 1977. Ohio State University's Big Ear Radio Telescope was conducting a routine survey of the sky, searching for signals that might indicate technological civilizations beyond Earth. The telescope operated automatically, scanning narrow bands of radio frequencies, printing out intensity readings on continuous paper. Astronomer Jerry Ehrman was reviewing the printouts 3 days later when he noticed something that made him grab a red pen. A signal had appeared, strong and narrow band, lasting exactly 72 seconds. The intensity was so far above background noise that Ehrman circled the alphanumeric sequence and wrote one word in the margin: "Wow." The signal came out the direction of Sagittarius, near the globular cluster M45. It was detected at a frequency of 1420 MHz, which sits within the protected radio astronomy band. No human transmissions are allowed at that frequency. The signal's bandwidth was narrow, less than 10 kHz, exactly what you'd expect from an artificial transmitter rather than a natural astronomical source. The Big Ear never detected it again. Follow-up observations found nothing. For nearly 50 years, the WOW signal has remained one of astronomy's deepest mysteries, until Avi Loeb decided to calculate where 3I Atlas was on that date. Working backward from the object's current trajectory and velocity, Loeb traced its path through space. In August 1977, 3I Atlas would have been approximately 600 astronomical units from Earth. That's 600 times the distance between Earth and the Sun, far out in the outer reaches of the solar system, but not yet in true interstellar space. The WOW signal originated from sky coordinates of right ascension 19 hours 25 minutes, declination minus 27 degrees. These coordinates point towards Sagittarius. Loeb calculated 3E Atlas's position on August 15, 1977. The object would have been at right ascension 19 hours 21 minutes, declination minus 19 degrees, 4 degrees separated in right ascension, 8 degrees in declination. In astronomical terms, that's remarkably close. The chance of two random directions in the sky aligning to within 9 degrees of each other, about 0.6%, but alignment alone doesn't prove causation. Loeb went further. If 3I Atlas transmitted the WOW signal, how powerful would it be? Need to be? The signal intensity detected by Big Ear ranged from 54 to 212 Janskys. A Jansky is a unit measuring radio flux density. For comparison, the strongest radio sources in the sky, like the Sun or Jupiter, typically measure in the hundreds to thousands of Janskys when observed at specific frequencies. At a distance of 600 AU, generating that received intensity would require a transmitter outputting between half a gigawatt and 2 gigawatts of power. That's the output range of a typical nuclear power reactor on Earth. Not impossible, not even particularly advanced by the standards of a civilization capable of interstellar travel, but notable because it's precisely the kind of power budget that would make sense for a deep space probe trying to communicate across vast distances. There's another detail. The WOW signal showed a slight frequency shift. It was detected at 1420, 4556 MHz, which is about 10 kHz higher than the neutral hydrogen line frequency. This represents a blue shift, meaning the source was moving toward Earth. 3I Atlas is moving toward the Sun at approximately 60 kilometers per second. When you account for Earth's motion and geometry in August 1977, the relative velocity would produce a blue shift. Loeb calculated the expected shift. It's close to what was observed, though not a perfect match. The difference could be explained by uncertainties in the exact position and velocity vectors, or by the signal having been transmitted in a specific direction rather than omnidirectionally. Here's where it gets interesting from a strategic standpoint. If you're an intelligence wanting to announce your presence, broadcasting near the hydrogen line makes sense. Hydrogen is the most abundant element in the universe. The 21 cm hydrogen line is so fundamental to radio astronomy that any civilization capable of radio technology would monitor it. It's the galactic calling card frequency. The WOW signal lasted 72 seconds because of how the Big Ear telescope operated. It used two feed horns, separated in the sky, that listened to adjacent regions as Earth's rotation swept them across the target. Each feed horn had a window of 36 seconds. The signal appeared in both horns sequentially, creating the 72-second detection. This means the source was transmitting continuously, or at least for the duration that Big Ear could observe it. Not a brief pulse, but a sustained broadcast. If 3I Atlas was responsible, this raises immediate questions. Was it a beacon, announcing presence to anyone listening? Was it a navigation pulse, marking position for some other spacecraft? Was it an attempt at communication, encoding information we lacked the sophistication to decode? Or was it entirely unrelated? A cosmic coincidence where an interstellar comet happened to be aligned with a natural radio source we haven't yet identified. The problem is, we don't have radio telescope data on 3I Atlas. Not from August 1977, obviously, but not from now either. No observatory has reported pointing radio dishes at this object. The focus has been on optical observations, on spectroscopy, on imaging. The questions being asked are about composition and structure, not about whether it's transmitting. Loeb is arguing that needs to change immediately. The object is approaching perihelion. It's getting closer to the sun, which means higher temperatures, more activity, more energy available if there's any kind of technological system involved. If it transmitted once at 600 astronomical units, if it's designed to communicate at specific points in its journey, this would be the time. Radio telescopes like the Very Large Array in New Mexico, the Arecibo successor facilities, even the vast arrays in China and Australia could monitor 3-eye atlas across multiple frequencies, not just the hydrogen line, but across the spectrum where artificial signals might appear. The observation would be straightforward. Point. Listen. Compare to background. Look for any narrow band signals, any modulation patterns, any repetitive structures that natural sources don't produce. If there's nothing, fine. It costs a few hours of telescope time to rule out the hypothesis. But if there's something, if 3-eye atlas is emitting radio signals, even faint ones, even intermittent ones, that changes everything about how we interpret this object. Because a comet doesn't broadcast. A chunk of ice and rock, even from another star system, doesn't generate radio signals at specific frequencies. Natural astronomical sources produce radio emissions, but they're broadband, chaotic, lacking the structure that indicates intention. The WOW signal had structure. It had a narrow bandwidth. It appeared at a meaningful frequency. And if Avi Loeb is right about the alignment, if the 0.6% coincidence is actually causation, then somewhere in the outer solar system 48 years ago, something transmitted a signal powerful enough for us to notice. That something is now racing past Mars, hidden behind the sun from our perspective, doing things that comets aren't supposed to do. The question isn't whether we should be listening. The question is why we aren't already. Chapter 4. It's making industrial alloys in space. When comets approach the sun, they begin to shed material from their surfaces. Ice sublimates directly from solids. To gas, dust particles lift off, trapped volatiles escape, and occasionally, if the comet gets hot enough, trace amounts of metals vaporize from the dust grains embedded into the ice. Nickel and iron appear together in these outgassing plumes, always together because they form together in stellar processes, exist together in meteoritic material, and sublimate at similar temperatures. The ratio varies slightly from comet to comet, but it follows a predictable pattern. For every atom of nickel you detect, you expect to see about 10 atoms of iron. The previous interstellar comet, 24I Borisov, followed this rule perfectly. Solar system comets follow it. Every icy body we've observed that shows metal emission follows it, except 3E Atlas. The European Very Large Telescope in Chile has been observing this object with its ultraviolet and visual Echelle spectrograph, an instrument designed to split light into its component wavelengths with extraordinary precision. Between August and September, observers captured spectroscopic data across 6 time periods as the comet moved from 314 astronomical units down to 214 astronomical units from the sun. In every observation window, nickel emission lines appeared in the spectrum. Bright, clear, unmistakable. Iron appeared only when the comet got closer than 2.64 astronomical units. Before that threshold, nickel without iron. After it, nickel with some iron, but in ratios completely unlike anything seen in other comets. The nickel to iron ratio measured orders of magnitude higher than solar abundance ratios, higher than typical cometary ratios, higher than natural geologic processes would produce. The production rate made it even stranger. 3. Atlas was releasing nickel gas at approximately 5 g per second when first observed. As it got closer and warmed up, that rate increased dramatically. 5 g per second doesn't sound like much until you consider what it means. That's 430 kilos per day, over 3 tons of nickel per week, from an object that's supposed to be made primarily of water, ice, and rock. The surface temperature at 2.8 astronomical units, where much of this emission was observed, sits far too low to vaporize silicate minerals or metallic grains that would contain nickel and iron. The comet would need to be at least twice as close to the Sun for normal sublimation of refractory materials to occur. Something else is happening. The research team proposed several possibilities. Perhaps nickel exists in a form that releases easily. Nickel tetracarbonyl, a volatile compound, breaks down under ultraviolet light and would release free nickel atoms into the coma. But forming nickel tetracarbonyl requires specific chemistry, specific conditions, specific pathways that aren't common in natural processes. On Earth, we produce nickel tetracarbonyl industrially. It's part of the MOND process, used to purify nickel from ore. You heat impure nickel with carbon monoxide at specific temperatures and pressures. The nickel forms gaseous nickel carbonyl. You then decompose it at higher temperatures to deposit pure nickel. The chemical signature of 3I Atlas releasing nickel without corresponding iron mimics the output of this industrial refining process. There's another possibility the researchers mentioned. Perhaps the nickel is embedded in organic compounds or exists as nanoscale particles that respond differently to solar heating than bulk metal grains. Perhaps photon, stimulated desorption, where light directly kicks atoms off the surface, is somehow preferentially releasing nickel. These are plausible, natural mechanisms, complex, requiring specific conditions, but possible. Except here's the thing about natural mechanisms. They leave evidence. They require precursor materials. They depend on the comet's formation history, its journey through space, the radiation environment it experienced. 3I Atlas likely formed in the Milky Way's thick disk, a region of older metal, poor stars. Models suggest it spent between 4 and 7 billion years traveling through interstellar space before entering our solar system. During that journey, it would have been exposed to cosmic rays, to background radiation, to collisions with interstellar dust and gas. Could that exposure have created surface chemistry exotic enough to explain the nickel emission? Could the comet have accumulated material during its journey that now, heated by the sun, releases metals in unusual ratios? You'd expect comets that formed around different stars to show chemical differences. Different protoplanetary disks have different compositions. The mix of elements, the ratio of volatile to refractory materials, the structure of organic molecules. All of this varies based on where and when a solar system forms. But the laws of physics don't change. Nickel and iron still form together in supernovae. They still condense together in protoplanetary disks. They still sublimate at similar temperatures. Getting them to separate to release in dramatically different ratios requires overcoming fundamental chemical relationships. Unless the nickel isn't sublimating from ice and rock, unless it's being released through a process that involves chemistry we don't typically associate with comets, Loeb, predictably, has pointed out that the observation matches what you'd expect from artificial nickel production. Not that the comet is a factory, but that if it were a technological object with nickel-based components, or a nickel-rich surface coating accumulated during interstellar travel, solar heating could ablate that material. The lack of iron would then simply reflect the composition of whatever is being eroded. The counter-argument is straightforward. Why would an advanced civilization build something out of materials that ablate so easily? If you're designing an interstellar probe to last billions of years, you don't use materials that start vaporizing the moment you get near a star, unless the vaporization is intentional, unless releasing a plume of material serves some purpose. Cooling, perhaps, mass shedding to adjust trajectory, signal generation, creating a visible marker that can be observed from a distance. Or unless the coating accumulated during the journey wasn't part of the original design. Interstellar space isn't empty. At 60 kilometers per second, even diffuse gas and dust particles impact with significant energy. Over millions of years, a spacecraft would accumulate surface material just like a comet does. If that material happened to be rich in certain elements based on what regions of the galaxy the object traversed, you might see unusual compositions. The Very Large Telescope. Data doesn't prove any of this. It simply establishes that 3I Atlas is behaving anomalously. The nickel without iron, the extreme production rates, the timing of when different emissions appear, none of it fits comfortably into our models of how comets work. And nickel is just one piece. Because while the VLT was documenting metal emissions, the Hubble Space Telescope was capturing images that revealed something even more fundamental. Something that challenges the very definition of what a comet is. Chapter 5. The Antitail. Anomaly comet tails point away from the sun. This is one of the first things you learn about comets, not because they're following the comet's motion, but because they're being pushed by solar radiation and the solar wind. Photons carry momentum. When billions of light, years of photons per second strike dust particles and ionize gas molecules, they transfer that momentum outward, creating the characteristic tail that always streams away from our star. Direction is so fundamental to comet behavior that when astronomers spot a comet, they can immediately determine which way the sun lies just by looking at where the tail points. On July 21st, the Hubble Space Telescope captured the highest resolution image yet obtained of 3I Atlas. The comet was 277 million miles from Earth, still inbound toward its October perihelion. The image shows a diffuse glow ahead of the object, pointing toward the sun. The glow is elongated roughly 10 times longer than it is wide, forming a teardrop or jet-like structure. Behind the object, in the direction where a tail should be streaming, there's nothing. No bright plume, no extended dust trail, just the faint gradient of scattered light fading into background darkness. The glow is an anti-tail. Now, anti-tails aren't completely unknown in solar system comets, sometimes under specific geometric conditions. When Earth passes through a comet's orbital plane, we see dust that's been left behind in the comet's orbit, stretching out in front of the comet from our viewing angle. It's an illusion of perspective, but 3I Atlas isn't in this geometric configuration. The viewing angle doesn't support a perspective effect, and the brightness profile of the forward glow doesn't match what you'd expect from orbital dust. David Jewett, an astronomer at UCLA who led the Hubble observations, analyzed the surface brightness as a function of distance from the nucleus. In a normal comet coma, brightness falls off gradually. Dust spreads out, dilutes, and the intensity drops following a gentle power law. The forward glow of 3I Atlas drops with a projected power law slope of -3. That corresponds to a three-dimensional emissivity profile with a radial slope of -4. This is steeper than observed in typical solar system comets. Much steeper. A steep fall off suggests that whatever is creating the glow is concentrated near the source and dissipates rapidly. Either the material is extremely fine, grained and quickly pushed away by radiation pressure, or there's active jetting from a specific location on the nucleus creating a directed plume. DeWitt's team interpreted this as dust evaporating from the sunward side of the comet. Solar heating would be strongest on the hemisphere facing the sun. Ice sublimates, dust lifts off. The dust cloud expands forward before radiation pressure begins to push it back. It's a reasonable interpretation, but it requires the comet to be shedding material asymmetrically, with the sunward side dramatically more active than the rest of the surface. That level of asymmetry is unusual, but not impossible. What's harder to explain is the absence of a dust tail. If dust is being lifted off the surface in quantities sufficient to create the visible forward glow, the dust should persist. Radiation pressure would push it outward. The comet's motion would draw it back into a tail. We should see something, unless the dust particles are extremely small. Particles smaller than a few hundred nanometers interact so strongly with light that they're blown away from the comet almost immediately, creating a faint haze rather than a distinct tail. But such small particles also get destroyed quickly by solar radiation, breaking down into even smaller fragments until they're essentially invisible. Or unless most of what we're seeing isn't dust at all, but gas. Gas doesn't form persistent tails the way dust does. It disperses, thins, becomes transparent once it moves far enough from the nucleus. But if it's primarily gas creating the forward glow, that brings us back to composition. Questions. What gas? At what rate? And why so concentrated in one direction? There's another possibility that Loeb and his colleague Eric Kito explored in a paper. If 3I Atlas is generating its own light rather than just reflecting sunlight, the brightness profile would look different. Internal energy sources, whether from radioactive decay or some other process, would create emission that falls off steeply with distance simply because you're moving away from the source. This isn't as wild as it sounds. Some comets show faint air glow in their comas, emission from molecules excited by solar ultraviolet light, but those emissions are well characterized. We know what wavelengths to expect, what intensities, what structures. The Hubble image is broadband. It captures light across a range of wavelengths. Without spectroscopy of that specific forward glow, We can't determine whether it's purely reflected sunlight or includes some emission component. What we can say is that the structure is anomalous: forward, directed, steep fall, off, no corresponding tail. These features together create a picture that doesn't fit standard comet models without invoking special circumstances. And here's what makes it important. The orientation of this jet or plume, or whatever we're calling it, points in the direction of motion. The comet is traveling toward the sun, and the glow extends ahead in that same direction. If you wanted to design a braking system for an interstellar object, releasing material forward would create thrust in the opposite direction. It's not efficient compared to rocket propulsion, but over long time scales with continuous mass loss, it could produce measurable deceleration. 3I Atlas has shown no measurable non-gravitational acceleration. Multiple teams have analyzed its trajectory, compiled thousands of positional observations, and found motion consistent with gravity alone. But that analysis has limits. Small accelerations below about 15 meters per day squared would be lost in the noise. And the observation window is relatively short. The comet was only discovered in July. We've tracked it for a few months across a portion of its orbit. If it were decelerating slowly, gradually adjusting its trajectory through directed mass loss, we might not detect it yet. Or the forward jet might be entirely natural, the result of how ice sublimates from a rapidly spinning nucleus within a regular shape. The image alone can't tell us, but combined with the other anomalies, the nickel emissions, the chemical composition, the trajectory, it adds to a pattern where each individual observation can be explained naturally, but the collective picture becomes increasingly strained. You can have a comet with unusual chemistry. You can have one with an odd trajectory. You can have one that outgases asymmetrically. But having all of these features in a single object, the third interstellar visitor we've ever detected, starts to push against statistical expectations, especially when you calculate just how massive this thing actually is. Chapter 6, 33. Billion tons of mystery. When an active comet releases gas and dust, physics demands a response. Action and reaction. Material ejecting from the surface creates thrust. Not much, but measurable. A typical comet might experience non-gravitational acceleration of a few hundred meters per day squared. Over weeks and months, this causes the trajectory to deviate from a pure gravitational path. Astronomers use these deviations to estimate how much mass a comet is losing, and by extension, how massive its nucleus must be. More massive objects resist acceleration. A small nucleus shedding material will veer noticeably. A large one barely budges. Between May 15th and September 23rd, 227 objects worldwide tracked 3I Atlas. More than 4,000 individual position measurements were compiled at the Minor Planet Center, the International Clearinghouse for Small Body Observations. Richard Clote, Peter Veers, and Avi Loeb analyzed this data set. They fitted the observations to a purely gravitational trajectory, calculating where the comet should be at each moment based solely on the sun's gravity and perturbations from planets. Then they looked for deviations. The upper limit on non-gravitational acceleration came out to less than 15 meters per day squared. Perhaps much less, perhaps even zero, but certainly below that threshold. This is astonishingly small for an active comet that's visibly outgassing. The James Webb Space Telescope detected carbon dioxide escaping from 3I Atlas at roughly 150 km per second in early August. That's 13 tons per day. As the comet moved closer to the Sun through September, that rate likely increased. When you eject mass at high velocity, conservation of momentum dictates that the remaining object experiences a force. The gas coming off the surface has an outflow velocity around 440 meters per second, measured by Webb's spectroscopy. Plug in the numbers, multiply mass loss rate by velocity, divide by the comet's mass. The result tells you how much the comet should accelerate. If 3I Atlas showed negligible acceleration, despite this continuous mass loss, its nucleus must be massive enough that the thrust becomes undetectable in the observational noise. The calculation yields a minimum mass of 33 billion tons. Think about that number. The first interstellar object, 1Gi Oumuamua, had an estimated mass somewhere between 10 million and 100 million tons, depending on a sum of about its density and shape. The second, 2I Borisov, likely weighed a few hundred million to a few billion tons based on its brightness and activity level. 3I Atlas is at least 33 billion tons, potentially more, since that's just the lower limit. It could be 10 times heavier and still fit the observations. This makes it 1,000 to 1,000,000 times more massive than the previous interstellar visitors. And here's where the statistics become uncomfortable. Models of how interstellar objects form and get ejected from planetary systems predict a size distribution. Small objects should vastly outnumber large ones. This isn't arbitrary. It's based on what we know about planet formation, about gravitational interactions, about how material gets flung out of solar systems. For every kilometer scale object floating through interstellar space, there should be thousands of objects 100 meters across. For every 100-meter object, thousands more at 10 meters. The distribution follows a power law. When we discovered 1Ia Oumuamua at roughly 100 meters in size, that was expected. Small objects are common. They're harder to detect because they're faint, but with telescopes scanning the sky continuously, we should find them. 2 Iberosov, larger and more active, fit the same framework. Bigger than Oumuamua, but still within the range of what models predicted we'd encounter. 3. Atlas breaks the pattern. Its minimum diameter, based on that 33 billion ton mass estimate, exceeds 5 kilometers. More realistically, given what we know about cometary densities, it's probably between 5 and 10 kilometers across. Objects this large should be extraordinarily rare. The models suggest we ought to detect somewhere between 10,000 and 100,000 smaller interstellar objects before encountering one this massive. We've detected Loeb calls this a major anomaly. The phrase undersells it. If 3I Atlas truly is 5+ kilometers across, and we're seeing it as only the third interstellar object ever identified, either our models of interstellar object populations are catastrophically wrong, or we're exceptionally lucky to the point of statistical absurdity, or 3I Atlas isn't a random sample from the expected population. The lucky hypothesis requires believing we hit a 1 in 10,000 or worse chance. Possible, but uncomfortable. The wrong models. Hypothesis means rethinking fundamental assumptions about how planetary systems form and evolve, about how objects get ejected into interstellar space, about the mass distribution of debris wandering the galaxy. Not impossible, but it would require major revisions to theories that work well for everything else we observe. The non-random hypothesis suggests 3. I-Atlas is unusual for reasons beyond statistics. Perhaps it formed through a rare process that produces large objects more frequently than standard planet formation models predict. Perhaps it's a planet forming seed, as some researchers have proposed, a large solid core ejected early in a solar system's history. Or perhaps it's following an intentional trajectory that brought it here, making its detection not a matter of chance, but of design. That last option is what makes most astronomers uncomfortable. Not because it's impossible, but because accepting it requires abandoning the principle that says we should exhaust natural explanations before invoking extraordinary ones. But here's the tension. At what point do the natural explanations become more extraordinary than the alternative? A comet that's 1 million times more massive than expected, that produces industrial metal signatures, that jets material forward with no backward tail, that glows green without the molecules that cause green glow, that aligns with a famous radio signal to within 1% probability, that follows a trajectory passing remarkably close to multiple planets. Each anomaly has a potential natural explanation. The combination strains credulity, and we still haven't discussed the single most bizarre aspect of its chemistry, the discovery that made headlines precisely because it violated every rule we have about what comets contain. Chapter 7. The Chemical Nightmare. On August 6th, the James Webb Space Telescope pointed its near-infrared spectrograph at 3I Atlas. Webb operates above Earth's atmosphere, free from the water vapor and carbon dioxide that plague ground-based infrared astronomy. Its instruments can detect molecules that would be invisible to telescopes on the surface. The spectroscopy revealed carbon dioxide, water, carbon monoxide, and carbonyl sulfide in the comet's coma, all expected for an active comet, but the ratios were profoundly wrong. The carbon dioxide to water ratio measured 8:1. In every other comet ever studied, including the previous interstellar Visitor 2 at Borisov, water dominates. Carbon dioxide exists as a minor component, typically making up 5 to 20% of the volatile inventory. Water ice forms the bulk of cometary material because water was abundant in the protoplanetary disks where comets formed. 3I Atlas inverts this completely. For every molecule of water, there are 8 molecules of carbon dioxide. By mass fraction, the coma is roughly 87% carbon dioxide, 9% carbon monoxide, and only 4% water. This ratio sits 6 standard deviations above the typical value for solar system comets. In statistical terms, that's not an outlier. That's a different population entirely. Martin Cordner, the astronomer who led the Webb observations, noted that such a high carbon dioxide content could indicate the comet formed near the carbon dioxide ice line in its parent protoplanetary disk. This is the distance from a young star where temperatures drop low enough for carbon dioxide to condense into solid ice. In our solar system, that line sits farther from the sun than the water ice line. Objects forming between these two boundaries would be carbon dioxide rich. But even then, you'd expect water to be present as a significant component, not reduced to a mere 4%. Another possibility involves radiation processing. 3. Atlas spent billions of years in interstellar space. Bombarded by cosmic rays, this radiation can alter surface chemistry, breaking apart water, ice molecules while leaving carbon dioxide relatively intact. Over enough time, you might create a surface layer enriched in carbon dioxide, but that would be a surface effect. Once the comet approaches the sun and begins shedding material, you'd expect to dig through the processed layer and start seeing more typical compositions underneath. The spectroscopy shows no sign of this transition. The carbon monoxide ratio adds another puzzle. At 1.4 times the water abundance, it's elevated, but not as dramatically as the carbon dioxide. Carbon monoxide is even more volatile than carbon dioxide. It sublimates at lower temperatures. If the comet was simply warming up and releasing ices in order of volatility, carbon monoxide should appear first and in high abundance. Instead, it's carbon dioxide that dominates, with carbon monoxide as a secondary component and water trailing far behind. This chemistry suggests formation conditions unlike anything in our solar system. Either the comet comes from a protoplanetary disk with radically different composition than the one that formed our planets, or it underwent processes during its journey that transformed its makeup into something we've never encountered. And then there's the polarization. When light scatters off dust particles, it becomes polarized. The degree and direction of polarization depends on the size, shape, and composition of the particles, as well as the angle at which you're observing. Astronomers use polarization to infer properties of cometary dust that are difficult to measure directly. A team led by Zach Gray observed 3I Atlas through polarizing filters over several weeks. They measured polarization as a function of phase angle, the angle between the sun, the comet, and Earth. The results were unlike any object in the solar system. 3I Atlas showed extreme negative polarization. At small phase angles, the polarized light was oriented perpendicular to what every other comet, asteroid, and dusty object displays. The magnitude of this negative polarization exceeded anything in the existing database. Negative polarization can occur when light scatters off particles with specific optical properties, but achieving the degree observed requires unusual combinations of size, composition, and structure. The dust grains would need to be larger than typical cometary dust, perhaps with complex internal structure or unusual refractive indices. Or the scattering isn't happening in the way we typically model. If the dominant light source isn't scattered sunlight, but includes emission from the object itself, polarization signatures change. Fluorescence from gases can produce polarization patterns different from pure dust scattering. But again, that requires explaining what's emitting light and why. The polarization study, the inverted chemistry from Webb, the carbon chain depletion that somehow still allows a green glow. These observations combine to paint a picture of an object that violates expectations at every level. You can construct scenarios where each finding individually makes sense. A comet from a carbon dioxide-rich formation region, dust with unusual optical properties from extended radiation exposure, surface chemistry altered by billions of years in space. But explaining all of them simultaneously in a single object requires stacking unlikely conditions on top of each other. The comet would need to have formed in exactly the right location to be carbon dioxide dominated, then been ejected at exactly the right time to spend billions of years in interstellar space accumulating radiation damage, then happen to collect dust during that journey with optical properties, unlike anything we typically see, then entered our solar system on a trajectory that brings it unusually close to multiple planets. The more specific the required conditions become, the less likely the scenario. And there's one more detail that deepens the mystery: the cyanogen detection. Cyanogen is a carbon-nitrogen compound. It's not uncommon in comets, but its presence is interesting because early observations detected it in 3I Atlas, while simultaneously showing a strong depletion of other carbon chain molecules like dicarbon and tricarbon. Lewis, Salazar Manzano, at the University of Michigan, analyzed spectra from Kitt Peak Observatory. His team found evidence for cyanogen emission before the comet was close enough to the Sun to be strongly active. This suggests cyanogen was present in volatile form near the surface, easily released with minimal heating. But cyanogen production in comets typically correlates with the presence of complex organic molecules and carbon chains. Finding one without the others is unexpected, like discovering smoke without fire. Unless the chemistry isn't following the pathways we assume, unless the molecules weren't created through the standard processes of comet formation and evolution, unless they were introduced through mechanisms we haven't considered, the chemical signature of 3I Atlas reads like a comet designed to confuse. Every measurement reveals properties that technically could be natural, but collectively strain the boundaries of what natural processes produce. And while chemists debate isotope ratios and spectroscopists argue over emission line profiles, Avi Loeb has been calculating something else entirely, something that makes the chemistry questions secondary to a more immediate concern about what this object might do next. Chapter 8: The Precursor Probe. Theory. Loeb began with a simple geometric calculation. 3I Atlas passed within 29 million kilometers of Mars on October 3rd. But that's not the closest it gets to Mars's orbital path. The minimum orbit intersection distance, a measure of how close one object's trajectory comes to another's complete orbital path, sits at just 2.7 million kilometers. 2.7 million kilometers sounds vast. It's roughly 7 times the distance between Earth and the Moon. But in orbital mechanics terms, especially for an object traveling at 60 kilometers per second, it's remarkably close. Close enough that a small adjustment in velocity could bring the comet into direct contact with Mars. Loeb calculated the numbers. A trajectory change of 10 to 15 km per second applied during September would shrink that closest approach distance to zero. The comet would impact Mars, or at minimum pass within the planet's atmosphere. Now, comets don't make trajectory changes that large. The outgassing thrust from a natural comet might produce velocity changes of a few hundred meters per second over months. Getting to 10 or 15 kilometers per second requires either a catastrophic fragmentation event or active propulsion. But here's what caught Loeb's attention. If 3I Atlas isn't a single object, if it's accompanied by smaller components, those components don't need to match the main object's velocity. A mothership releasing smaller probes can impart significant relative velocity. The probes separate, following slightly different trajectories. While the main object passes Mars at 29 million kilometers, a probe with the right velocity vector could reach the planet. The Webb telescope measured the outflow velocity of gas, leaving 3A Atlas at 440 meters per second. That's the speed of material naturally vaporizing from the surface. But if something were deliberately ejected, if a probe separated from the main body using mechanical force rather than thermal evaporation, it could achieve much higher speeds. A velocity of 10 kilometers per second isn't unreasonable for a separation maneuver. It's well within the capability of conventional rocket propulsion. Even a simple spring, loaded release mechanism, could impart a few kilometers per second to a small object. So, Loeb asked, if 3I Atlas released precursor probes in September, could they reach Mars? The answer is yes. Depending on timing and direction, a probe could arrive at Mars anywhere from a few days to a few weeks after separation. Now, we need to think about what that means practically. The Heresy camera on Mars Reconnaissance Orbiter was looking for 3I Atlas. It was calibrated to detect an object 5 to 10 kilometers across at 29 million kilometers distance. But HIRES was designed to image Mars' surface. It can resolve features down to 30 centimeters. If a smaller object, say 100 millimeters long, passed closer to Mars, within even a few 100,000 kilometers, HIRES might detect it, except HIRES was pointed at the expected position of the main comet. If a precursor probe came from a different angle, took a different path, it could approach Mars unobserved by the spacecraft specifically watching for 3I Atlas. The Perseverance rover's sky observations become more interesting in this context. Those images showing possible multiple objects, the ones Stephen Burns and others analyzed, were taken during a window when both the main comet and any potential companions might be visible. If there were multiple fast-moving objects in those images, if that's not just processing artifacts or background noise, we might be seeing evidence of a dispersed system rather than a single compact nucleus. Loeb took the calculation further. He considered what happens after perihelion, after the comet swings around the sun and emerges on the other side. The object will be hidden from Earth. Based observation from late October through most of November. It reaches perihelion on October 29th at a distance of 202 million kilometers from the Sun. During that closest approach, it will be experiencing maximum solar heating, maximum radiation pressure, maximum stress on any structural components. If it's a natural comet, this is when we'd expect to see dramatic changes, increased activity, possible fragmentation. The nucleus could split, releasing fresh ice that dramatically brightens the coma. Outgassing rates could spike as subsurface volatiles reach critical temperatures. If it's something else, if it's capable of maneuvering, perihelion offers a strategic opportunity. The gravitational assist from passing close to the Sun could be used to alter trajectory. A small velocity change at perihelion translates to large position differences months later. This is how spacecraft use gravity assists to reach distant destinations efficiently. Loeb noted that with appropriate thrust at perihelion, 3I Atlas could adjust its path to intercept Earth. The object will be traveling retrograde, opposite to the direction planet's orbit. This geometry offers advantages for an intercept trajectory. You're not chasing a target. You're timing the collision between two objects moving toward each other. A velocity shift of 30 for 40 kilometers per second during October could bring 3I Atlas, or components of it, to Earth between late December and early January. Is 40 kilometers per second achievable? For a natural comet, absolutely not. For a spacecraft with propulsion, it depends on the mass and the engine. Chemical rockets would struggle with those numbers for something as massive as 3I Atlas. But we're talking about technology that potentially crossed interstellar space. Propulsion systems we can barely imagine. Loeb was careful in how he phrased this. He didn't claim 3I Atlas would maneuver toward Earth. He pointed out that the opportunity exists. That if the object has capability, this is when and how it would use it. And then he added something that got picked up by every news outlet covering the story. If 3I Atlas maneuvers toward Earth when it reappears from behind the sun, financial markets may crash. Think about what that statement implies. Not just the immediate panic from news of an object heading toward our planet, but the deeper implications. Confirmation that we're dealing with technology, that something artificial crossed interstellar space and is now approaching Earth, that we're not alone, and that whatever is out there knows we're here. Markets crash on uncertainty, on fundamental shifts in how we understand the world. The discovery of artificial interstellar technology would be the most profound uncertainty in human history. Even if the object posed no direct threat, even if its intentions were entirely benign, the knowledge that advanced civilizations exist and can reach our solar system would reshape every assumption underlying our economic, political, and social systems. Loeb's statement wasn't fear-mongering. It was recognition that the implications extend far beyond astronomy. This is why the Mars observations matter so much. This is why the silence from NASA and ASA feels significant. Because right now, 3I Atlas is approaching the point where, if it's going to do something unexpected, this is the window. And we won't know what happened until it emerges from solar occultation weeks from now, potentially having changed course, potentially having released objects we can't track, potentially having demonstrated capabilities that force us to abandon the comfortable assumption that it's just an unusual comet. The Trojan horse, Loeb calls it, an innocent-looking visitor that could carry devastating consequences hidden within its apparently natural exterior. Chapter 9. Behind the Sun, the Danger Window. Loeb creates a scale. He calls it the Loeb scale, a ranking system from 0 to 10 that quantifies how likely an object is to be artificial rather than natural. 0 means definitively natural. A chunk of ice and rock following predictable physics with chemistry that matches known processes. 10 means definitively artificial. An object that displays unambiguous technological signatures, that maneuvers in ways requiring propulsion, that emits signals or exhibits structure impossible to explain through natural means. Most objects sit at 0. Asteroids, comets, meteoroids, all the debris wandering through space scores 0 because nothing about them suggests technology. 1. Oumuamua, the first interstellar visitor, Lobe A ranked somewhere between 3 and 5, depending on which observations you emphasize. Its unusual shape, its non-gravitational acceleration without visible outgassing, its tumbling motion. These features pushed it above 0, but not high enough to claim certainty. 3I Atlas Lobe currently ranks at 4, not 0 because the anomalies are too numerous. The trajectory alignment with planets, the chemical inversions, the nickel without iron, the forward jet with no tail, the mass discrepancy. Each individually might be natural, but collectively, they elevate the probability of something more. Not 10, because we lack definitive proof. No detected radio signals, no observed maneuvers, no photographs showing geometric structures. The object still behaves enough like a comet that natural explanations, however strained, remain possible. 4. Sits in the uncertain middle, more likely than not to be natural, but with enough unusual features that the artificial hypothesis can't be dismissed. But that ranking could change dramatically based on what happens over the next few weeks. October 29th marks perihelion. The comet reaches its closest point to the Sun at roughly 1.4 astronomical units, just inside Mars' orbital distance. At that moment, from Earth's perspective, it will be directly behind the Sun. The Sun's angular diameter in our sky is about half a degree. 3I Atlas will pass within that glare zone. Ground-based telescopes can't observe it. Space-based observatories like Hubble and Webb need to avoid pointing too close to the Sun to protect their sensitive instruments. We go blind. The blackout extends from late October through most of November. The exact dates depend on viewing geometry and how bright the comet becomes. But conservatively, we lose direct observation for at least 3 weeks. 3 weeks where the object experiences peaceful heating, where any thermal stresses reach maximum, where, if it's technological, it has privacy to do whatever it's designed to do. When it emerges, we'll be looking for changes. Brightness is the first indicator. If the comet fragments or undergoes a major outburst, it will brighten significantly. Solar system comets sometimes increase in brightness by several magnitudes during perihelion passage. If 3I Atlas does the same, it suggests natural processes are dominant. If it doesn't brighten, if it remains relatively stable, or even dims, that's interesting, it might indicate a more durable structure, less vulnerable to thermal stress than typical comets. Trajectory is the second indicator. If the object emerges on a path consistent with gravitational predictions, following the orbit calculated from pre-perihelion observations, that supports the natural interpretation. If there's any deviation, any change in velocity, or direction not explained by gravitational perturbations, that moves it up the Lobe scale quickly. Spectroscopy will reveal compositional changes. Did the surface chemistry shift? Are new materials exposed? Is the ratio of volatiles different from what we measured before? And structure? When 3I Atlas becomes visible again in early December, telescopes will immediately photograph it. Does it look the same? Is the forward jet still present? Is there evidence of fragmentation or splitting? Meanwhile, Lobe isn't just calculating possibilities, he's watching the sky. The Galileo project operates 3 observatories, one in Massachusetts, one in Pennsylvania, one in Nevada. They're equipped with wide field cameras, infrared sensors, and automated detection algorithms designed to identify aerial phenomena that don't match conventional aircraft or natural objects. The project's primary focus is unidentified anomalous phenomena, UAP, what used to be called UFOs. But with 3I Atlas approaching perihelion, Loeb has added a specific monitoring protocol. If the object is a mothership, if it releases smaller probes toward Earth as it swings around the sun, those probes would arrive weeks to months later. December through January becomes the window where unexplained aerial activity might spike. The Galileo Project instruments will be running continuously, logging anything unusual, checking for patterns, looking for objects moving faster than satellites, displaying flight characteristics beyond current aerospace technology, appearing in numbers, or with timing that correlates to 3I Atlas's perihelion passage. It sounds like science fiction. It is science fiction in the sense that we're discussing scenarios pulled from speculative stories. But the difference is, we're doing it with real data, real calculations, real objects that we can photograph and measure. If Loeb is wrong, if 3I Atlas is simply an unusual comet, and all the anomalies have boring explanations, the Galileo project will detect nothing unusual. The object will emerge from behind the sun slightly brighter, possibly fragmented, following its predicted path. The nickel emissions will be explained through some exotic chemistry. The trajectory alignment will be recognized as selection bias, in which interstellar objects we notice that life continues, if he's right, if even partially right. December becomes one of the most significant months in human history. Not because of invasion scenarios or hostile intent. Loeb is careful to avoid that framing. Even artificial objects can be benign, scientific probes from civilizations with no interest in interference. But because confirmation changes everything, every assumption about our place in the universe gets rewritten. Every question about whether we're alone gets answered. Every decision about how we allocate resources, how we think about our future, gets made in a context where we know that crossing interstellar space is possible, that other intelligences exist, that we are, in the most profound sense, not special. ESA's JUICE spacecraft, currently on its way to Jupiter, will observe 3I Atlas in late November. Between November 2nd and 25th, JUICE will point its instruments at the comet just after perihelion, when it's emerging from the sun's glare, but still extremely active. JUICE carries cameras, spectrometers, and particle sensors. It's farther from the comet than Mars was, but it has the advantage of observing during peak activity when signatures are strongest. The data from JUICE won't arrive until February. The spacecraft is on the far side of the sun from Earth, using its high-gain antenna as a heat shield, communicating through a slower backup system. So we wait months for those observations to download and process. But they're coming. And they might show us what 3I Atlas was doing while hidden from Earth, what it looked like at its most active moment, whether anything changed that we need to understand. For now, though, we're in the dark, literally and figuratively. The object that's been puzzling astronomers for months is about to become invisible. hidden behind the overwhelming brightness of our star, doing whatever it does when nobody's watching. And when it comes back, if it comes back different, if it shows any sign of having done something intentional, Loeb's ranking moves from to 5, maybe higher. And the questions we've been asking about whether it could be artificial shift to questions about what it wants and what we should do about it. Chapter 10. What We're Not Being Told. There's a standard rhythm to how space agencies communicate discoveries. Press releases get drafted. Scientists give interviews. Raw data populates public archives. Social media accounts share highlights. The process is designed to be transparent, to build public interest, to justify the funding that makes these missions possible. When that rhythm breaks, when scheduled observations happen, but results don't appear, when questions get deflected with vague statements about ongoing analysis, people notice. NASA's official page for 3I Atlas lists assets that observed or plan to observe the object: Hubble, Webb, TESS, Swift, Spherex, Perseverance, Mars Reconnaissance Orbiter, Curiosity, Europa Clipper, Lucy, Psyche, Parker Solar Probe, Punch, SOHO, and ESA's JUICE. It's an impressive array. Practically every functional space telescope and planetary mission got pointed at this object at some point, but the data releases don't match the observation schedule. Webb's spectroscopy from August appeared quickly, published as a preprint within weeks. Hubble's July image became public. Spherex results on carbon dioxide emissions were shared. Then October hit, and the flow stopped. The Mars observations from October 1st through 7th should have been the easiest to release. Mars orbiters routinely make their images public within days. The high-risk website typically updates with new Mars surface photos every few days, sometimes daily, during active observation campaigns. Yet nothing from the 3I Atlas flyby has appeared. ESA operates under different administrative structures than NASA, different funding sources, different oversight, different public communication requirements. When both agencies go silent simultaneously on the same target, it suggests coordination. Coordination can mean collaboration. Scientists from both agencies working together, agreeing to wait until all data is analyzed before making statements. This is reasonable. For complex observations where preliminary results might be misinterpreted. Or coordination can mean consultation, discovering something unexpected that requires discussion about how to present it, what context to provide, what additional verification to complete before going public. The silence from Simeon Schmaus, the astrophotographer, who claimed to see early glimpses in October 1st images, adds another layer. Amateur observers typically share their findings eagerly. The community thrives on rapid discussion, on crowdsourced verification, on collaborative analysis. When someone goes quiet after making an intriguing claim, it usually means one of two things. Either they found an error and are embarrassed, or they found something significant and are preparing a more detailed presentation. Schmaus hasn't retracted his observations. He hasn't posted corrections. He simply stopped commenting. Meanwhile, amateur astronomers continue working with whatever data is available. The publicly posted Perseverance images from those October nights remain accessible. Anyone with image processing software can download them, stack them, look for moving objects. Multiple independent analysts have now reproduced Stephen Burns' finding of at least one fast-moving object consistent with 3I Atlas. The debate focuses on whether additional objects are present. Some see them clearly. Others attribute the apparent additional lights to artifacts from stacking algorithms, to cosmic ray hits that coincidentally appear near the comet's path to background asteroids. Without the high-resolution data from HIRS and the ESA orbiters, without official confirmation or denial, the question hangs unresolved. What we're seeing is a pattern. Official channels constrained by review processes and institutional caution. Amateur observers filling the gap with varying degrees of rigor and reliability. And an object that continues generating more questions than answers. Consider what we still don't know, despite months of observation: the exact size of the nucleus. Estimates range from less than 1 kilometer to over 10 kilometers, depending on assumptions about albedo and whether we're seeing primarily the nucleus or an extended dust coma. The rotation rate. Some observations suggest rapid rotation, others show no clear periodicity. Understanding how fast it spins tells us about structural integrity, about whether it's a single solid body or a loose aggregate. The source regions of outgassing is material venting from discrete jets or from broad areas of the surface. Discrete jets suggest localized volatile deposits or structural features. Broad emissions suggest a more uniform surface composition. The degree of fragmentation, if any, has the nucleus split into multiple pieces? Are there companion fragments traveling alongside the main body? Or is it structurally intact? These are fundamental questions that the Mars observations were supposed to answer. High rise at 30-kilometer resolution should easily distinguish between a single compact object and a fragmented or multi-component system. The spectroscopy from Mars Express and ExoMars should reveal regional composition variations if they exist. The instruments functioned. The observations were executed. The data exists somewhere in agency archives. We're just not seeing it. There is innocent explanations, data pipelines genuinely backed up by technical issues, scientists conducting thorough analysis before making statements. Bureaucratic delays unrelated to the content of the observations. There are less innocent explanations. Uncertainty about how to characterize unexpected findings. Consultation about whether preliminary observations warrant broader discussion before formal publication. We don't know which category applies. That's the problem. The absence of information creates a vacuum that speculation fills. What we can say with certainty is that the next few weeks matter enormously. 3I Atlas will emerge from behind the sun in late November or early December. Ground-based telescopes will immediately photograph it. Amateur astronomers will be watching. Professional observatories will allocate time if it looks the same, if its trajectory matches predictions, if its brightness and spectral signature remain consistent with what we measured before. The natural comet explanation strengthens considerably. If anything has changed, if there's evidence of maneuvering or structural modification, or unexpected brightening or new compositional signatures, the artificial hypothesis gains support. JUICE will observe it in late November during peak post-perihelion activity. Europa Clipper, currently en route to Jupiter, might also get observations depending on geometry and mission priorities. These spacecraft see the comet from angles and distances unavailable to Earth-based instruments. Their data will eventually arrive, eventually be processed, eventually inform our understanding. But eventually isn't now. Right now, we're in a gap between what's been observed and what's been shared, a gap between amateur discoveries and official confirmation, a gap between the questions we're asking and the answers that exist somewhere in data files we can't access. And while we wait in that gap, 3i Atlas continues its journey approaching the sun, heating up, becoming more active, potentially doing things we won't know about until weeks from now when it reappears and we see what changed. So, here we are, waiting, watching an empty sky where something extraordinary is hidden behind our sun. 3i Atlas is out there right now, closer to our star than it's been in billions of years, absorbing gigawatts of solar energy, potentially fragmenting, potentially maneuvering, potentially doing nothing more dramatic than what comets have done since the solar system formed. We've traced its path from the outer reaches of space, calculated where it was when the WOW signal reached Earth, measured the impossible ratios in its chemistry, documented the metals that shouldn't be there, mapped the tail that points the wrong way. We've counted the statistical improbabilities, stacked the anomalies, and arrived at a place where certainty feels impossibly distant. Maybe it's just a comet. An unusual one, granted, but ultimately a natural object following natural laws. The anomalies will resolve, the missing data will appear and clarify. December will come and the object will look exactly as expected, slightly brighter, following its predicted path, confirming that the universe still makes sense. Or maybe we're watching something that will rewrite every assumption we have about our place in the cosmos. Either way, the next few weeks will tell us, and we'll be here when they do. Thank you for staying with this story, for following these questions into uncertainty, for being willing to sit with mystery instead of demanding easy answers. If you found this valuable, consider liking and subscribing so you're here when the object emerges and we finally learn what we've been looking at. As always, this content is for educational and entertainment purposes. The science is real, the observations documented, but the interpretations remain speculative. We're exploring possibilities, not making definitive claims. Do your own research. Question everything, including what you've heard here. For now, 3i Atlas moves in silence behind the sun. December approaches. The amateur telescopes are ready. The professional observatories have time allocated. The Galileo Project instruments are recording. And somewhere out there in the darkness, an object from another star carries on its journey, indifferent to our questions, our theories, our hopes and fears about what it might represent. Sleep well, dream of distant stars, and remember that the universe has always been stranger than we imagined. Good night.